This dot looks harmless. But if this were a black hole, it would be one of the most extreme objects the universe allows. That circle is the important part. Not because it is a surface you could land on, but because it marks a point of no return. Cross it, and as far as the outside universe is concerned, you are not sending a postcard back. Black holes sound like one kind of thing, but they are really a whole family. Some are born from dead stars. Some sit at the centers of galaxies. Some might have formed in the first moments after the Big Bang, though we have not confirmed those yet. So today, we are sorting the whole black hole family tree. By the end, you will know the main types, how they form, which ones are real and observed, and which ones are still more like physics suspects on a cosmic evidence board. A black hole is not exactly an object in the normal sense. It is a region of space-time where gravity is so intense that inside a boundary called the event horizon, nothing can escape outward, not even light. That does not mean black holes are cosmic vacuum cleaners. If the sun magically became a black hole with the same mass, Earth would not instantly get sucked in. We would keep orbiting the same mass from the same distance, although we would have much bigger problems, like the missing sunlight. The key ingredients are mass, size, and density. Squeeze enough mass into a small enough volume, and space-time curves so severely that all future paths inside the horizon point deeper inward. This drawing is not perfect, but it helps. A black hole is not just strong gravity. It is gravity changing the available directions that anything can travel. The first major category is stellar mass black holes. These are usually a few to maybe dozens of times the mass of the sun, though the exact ranges depend on formation history and measurement. They form when very massive stars run out of fuel. The star can no longer hold itself up against gravity, the core collapses, and if enough mass remains, a black hole is born. We often detect these black holes when they are in binary systems, pulling gas from a companion star. That gas heats up and can shine in X-rays before crossing the horizon. Next are intermediate mass black holes. These are the awkward middle children, heavier than stellar black holes, but lighter than supermassive ones. Think hundreds to hundreds of thousands of solar masses, depending on the definition being used. They are important because they may be missing links. If small black holes can merge and grow, maybe intermediate black holes help explain how supermassive black holes got so huge. But compared with stellar and supermassive black holes, the evidence is still thinner and harder to interpret. This is one of the active mystery zones. Now the giants, supermassive black holes. These range from millions to billions of times the mass of the sun, and they live in the centers of many large galaxies, including our Milky Way. The Milky Way's central black hole is called Sagittarius A star. We have measured stars whipping around it, and the Event Horizon Telescope has produced an image-like reconstruction of the glowing material around its shadow. Supermassive black holes can power quasars and active galactic nuclei when they feed on surrounding gas. The black hole itself is dark, but the material falling toward it can become incredibly hot and bright. Finally, the speculative category, primordial black holes. These would not come from stars. They would have formed from dense regions in the very early universe. They could, in theory, have many possible masses, from tiny to enormous. But so far, primordial black holes are hypothetical. They are interesting candidates in some dark matter discussions, but they are not confirmed as the answer. Dotted box means possible, not proven. Now, mass is one way to classify black holes. But physicists also sort them by three properties: mass, spin, and electric charge. A simple, non-spinning, uncharged black hole is called a Schwarzschild black hole. It is the clean classroom version. A spinning black hole is called a Kerr black hole. This is probably more realistic because stars rotate, galaxies rotate, and collapsing material tends to carry angular momentum. Spinning black holes can drag space-time around them, an effect called frame dragging. Around a rotating black hole, there is a region called the ergosphere, where space-time itself is being pulled around so strongly that staying still relative to distant stars is not possible. Charged black holes are allowed in the math, but large astrophysical black holes are not expected to keep much net electric charge for long because they would attract opposite charges from their surroundings. So if the universe hands you a real black hole, spin is probably part of the story. There are three main formation arrows. Arrow 1, massive star collapse. This is the basic stellar route. A huge star burns fuel, builds heavier elements, loses the pressure support that held gravity back, and its core collapses. Depending on mass and details, the result may be a neutron star or black hole. Arrow 2, mergers. Black holes can collide and merge. We have detected gravitational waves from merging black holes, which are ripples in space-time produced by violent accelerating masses. This is one way black holes grow, and it gives us a new kind of astronomy. Not light, but space-time vibrations. Arrow 3, gas and cosmic growth. Supermassive black holes grow by accreting gas and by merging with other black holes and galaxies. But there is still an open question. How did some become so massive so early in cosmic history? One idea is direct collapse, where huge clouds of gas in the early universe may have collapsed into massive black hole seeds. Another is growth from smaller seeds. The evidence is still developing, so we should keep the confidence dial below case closed. Now for the strange shelf. Tiny black holes are possible in theory. If very small black holes exist, Hawking radiation predicts they should slowly lose mass, with smaller ones evaporating faster. But we have not confirmed naturally occurring micro-black holes, and particle collider fears about making dangerous ones are not supported by mainstream physics. A white hole is like the time reverse of a black hole in some mathematical solutions. Things can come out but not go in. That sounds amazing, but white holes have not been observed, and it is not clear that nature actually makes them. So, math possible does not mean universe approved. A black hole hides its central singularity behind an event horizon. A naked singularity would be a singularity without that horizon. Some equations allow possibilities like this, but many physicists suspect cosmic censorship may prevent them in realistic situations. That is still a deep and technical question, not a settled YouTube comment knockout. Some ideas from quantum gravity suggest black holes may not contain classical singularities in the simple way general relativity predicts. Proposals like fuzzballs or gravistars try to describe ultra-compact objects differently. These are fascinating but not confirmed replacements for ordinary black holes. The honest label is frontier physics. So here is the clean map. By mass, black holes come in stellar, intermediate, supermassive, and possibly primordial types. By properties, they can be described as non-spinning, spinning, charged, or combinations of those, though real astrophysical black holes are expected to be mostly about mass and spin. By origin, they can form from collapsed stars, mergers, gas growth, maybe direct collapse, and maybe early universe density fluctuations. And by weirdness, they force us to ask where general relativity ends and quantum physics begins. A black hole is not just a thing that sucks. It is a place where our best ideas about gravity become extreme enough to test themselves. Some black holes are confirmed cosmic residents. Some are likely but hard to find. Some are still mathematical invitations. That is what makes them so useful. Black holes are not just monsters in space. They are laboratories with no walls. So here is the brain nest question. If you could send one perfectly protected probe to study any black hole type, would you send it to a nearby stellar black hole, Sagittarius A star, a possible intermediate black hole, or a hypothetical primordial black hole? Drop your choice in the comments and tell me what you would want the probe to measure first.